This is the second of two videos on methods to compute the antiderivatives of products of trigonometric functions. In the previous video, link in the description, I look at functions of this form, a power of sine times a power of cosine. If at least one of the two exponents is odd, we already found a method that works. But if both exponents are even, we did not have a solution yet. That will be the point of this video. For instance, the simplest example is the integral of sine squared. How do we compute it? Before giving you the answer, I want to address something else. Is this an important problem? I am looking at a very specific family of functions. Are these integrals particularly important? My opinion is that in this problem, the journey is more important than the destination. In the past, mathematicians developed algorithms and methods to integrate many specific families of functions. These integrations appeared often in math, science, and technology, so they were useful. But this is a bit obsolete now. Today we have computer algebra systems for complex calculations and nobody integrates by hand. Well, somebody still needs to understand the method in order to program the computer, but that's it. However, there is still some value. We should look at these calculations as exercises in problem solving. That's where their value comes from, rather than from the usefulness of the specific integrals. How do I take a big complex problem, break it into cases, and use creativity to put together various algorithms? Okay, back to the problem. How do I integrate a power of sine times a power of cosine when both exponents are even? Fair warning, these questions can get long very quickly, so I am not going to solve the examples in full detail. I will just explain enough to convince you that there is a path, that if necessary we can complete the steps and get to an answer. Then I will stop. There are at least two standard approaches. The first method is to use the half-angle identities. Sine squared of x is 1/2 of 1 minus cosine of 2x, and cosine squared of x is 1/2 of 1 plus cosine of 2x. I assume you learned this in high school. Why are they useful? For the purpose of integration, I would rather have cosine of 2x than cosine squared of x. Cosine squared is harder to integrate, but cosine of 2x is as simple as cosine of x. For example, to integrate sine squared of x dx, I can use the half-angle identities and write it as 1/2 of the integral of dx minus 1/2 of the integral of cosine of 2x dx. Both these integrals are simple. I trust you can finish it from here. The same method will work for higher even powers. For example, what can I do with sine to the 4 times cosine squared? Well, I can write sine to the 4 as sine squared squared, and then I can use the half-angle formulas. Then I expand it. I will get a sum of a bunch of terms, and they all have lower exponents. I will need to look at those terms one by one. Some will be easy to integrate, others may have an odd exponent, and I can use the method from the previous video in that case. Others may still have an even exponent, and I can use half-angle formulas again. I warned you that this could get messy. As I said, I am not going to finish it. My goal was only to convince you that this gives us a path, perhaps a long path, that we can use to get to the final answer if we really need to. As a challenge, can you integrate sine to the 4 using this method? The second method is to use integration by parts creatively. This is sometimes longer and sometimes shorter. For example, say I want to integrate sine squared again. I can write sine squared of x as sine of x times sine of x, a product. As a reminder, here's the formula for integration by parts. I can use it if I choose u as sine of x and dv as sine of x dx. A derivative of sine of x is cosine of x, so du is cosine of x dx. And an antiderivative of sine of x is minus cosine of x, so v is minus cosine of x. Okay then. The integral of u dv, the integral of sine of x dx, is u times v, which is minus sine of x cosine of x, minus the integral of v du, which is minus cosine x dx. There, let's keep the identity and remove the process. I have proven that the integral of sine squared is minus sine times cosine plus the integral of cosine squared. How does this help me? I know another relation between sine square and cosine square. They add up to 1, so their integrals add up to the integral of 1, which we can easily compute. And now look at that. I can think of this as a system of two equations, and I can solve for the integral of sine squared. I won't finish it. I trust that from this point you see that we can get to an answer. The same method can in principle be used for any other integral of a product of even powers of sine and cosine, although it can easily get messy. As a challenge, can you integrate sine to the 4 with this method? If you find these kinds of questions interesting, then I recommend you watch the movie or read the book Hidden Figures. The main characters were human calculators during World War II. Now you understand some of the calculations that they had to do.